All right, so here's the continuation of section 10.1. So we've been using the law of sines on triangles where we have certain information given. There is a case where your answer might not be so clear-cut, and this is called the ambiguous case. It happens when you're given two sides and the non-included angle. In that instance, we can end up with 0, 1, or 2 triangles for our answer. So it's kind of an odd scenario here, but basically, let me grab a piece of paper real quick and see if I can sketch this real quick. So if we have two sides and a non-included angle, so let's see, let's say we have this side, and let's say that we've got that angle locked in. Okay, so it's the non-included angle. This right here can kind of swivel to where, we can have like no solution, we can have one solution, or we can have two different solutions. Because this length right here can vary and this angle can vary, we get this kind of swiveling action that might be able to form, like say, an acute and then an obtuse triangle by changing this angle and this length right here. If I had my book handy, I could show you. They have a pretty good sketch of how that plays out. But I want to show you algebraically how that happens. So you don't have to remember that it's going to be two sides in the non-included angle. I just want to show you that once you start using the law of sines, here's where, the stuff's going to get weird, okay? So if we want to solve the triangle with A equals 2, C equals 1, and gamma equals 50 degrees. So we start off by setting up the law of sines. We're going to have sine gamma over C and sine alpha over A, of course, because we have C and gamma and we have A. So we cross multiply, and we get A sine gamma equals C sine alpha here. Oh, sorry, we need to plug in first, my bad, before we start cross multiplying. So I'm going to plug in the 50 degrees for gamma, and C is 1, A is 2, and then we're going to cross multiply. So we'll get 2 sine 50 equals sine alpha. Then I'm going to take the inverse sine of that quantity, and I get the inverse sine of this 2 sine 50 is 1.532. When you go to take the inverse sine of this, because this quantity is bigger than 1, you're not going to have a solution. You're going to get a domain error. That's because the sine function doesn't go above 1. So that means there's no solution. So no triangle can be formed with this information. So here's what this looks like. We have C equals 1, we have A equals 2, and then we have a locked-in 50-degree angle over here. These three things are locked into place. So what can change? Well, this little piece over here can swivel around, and this piece right here can change lengths. It can be short, it can be long, but no matter what we do, no matter how short or long this side is, and no matter how we swivel this one, because we can't make it any longer, it's locked in with that length, we're never going to form a triangle out of that. So that's how we get this no solution. All right, so I just wanted to show you that if that happens, it could be that you did it correctly, and it's just not possible to form a triangle with that information. All right, so let's do another one of this type. So we have A equals 3, B equals 2, and alpha equals 40 degrees. So let's start off with the law of sines. We have sine alpha over A, sine beta over B. So just ignore this for now. We'll come back to it. Plugging in alpha, A, and B, and then cross multiplying, get 2 sine 40 equals 3 sine beta. Divide both sides by 3. And then I'm going to take the inverse sine of that amount right there. So this amount right here is this 0.428525. Take the inverse sine of that, and I get that beta is 25.37. That's an angle in quadrant 1. All right? From there, we have alpha, which was 40 degrees. We just found beta to be 25.37, so we can use the fact that the three angles add up to 180 to find gamma. And then now that we have gamma, we can use another version of the law of sines to find the value of C. So we have sine alpha over A, sine gamma over C, plugging in for alpha and A from the original problem, the gamma that we just found, cross multiply, and we get that C is about 4.24. Looks easy enough, right? Looks similar to the ones that we just did. Here's the catch, though. There could be a second triangle. It is possible in these instances where you might have a second triangle formed. That's because this inverse sine right here, this angle could be in quadrant 1 or it could be in quadrant 2 and be an obtuse angle. So this 25.37 degree angle, if I put it over here as a reference angle in quadrant 2, that would be 154.63 degrees. That might be a possibility. That might give us a second triangle from that information. It might be the information given it's capable of forming two different triangles. So here's what we check. We take this angle we just found, we add it to the angle that was given, and we compare it to 180. So if I take this 154.63 and I add 40 degrees, I get, what, 194.63? That's bigger than 180. Not possible for a second triangle, because we know that the three angles have to add up to 180. So if this angle, this possible second angle, plus the given angle, if it's less than 180, then we're going to have a second triangle. If it's bigger than 180, we're not going to have a second triangle. So I'm going to show you with the next example how that's going to go. All right, so all of these have that same two sides and a non-included angle kind of form to them. You know, if you find that kind of stuff helpful. So let's solve the triangle where A is 6, B is 8, alpha is 35 degrees. All right, we start off with the law of sines. We're going to plug in for alpha, A, and B so that we can solve for beta. We're going to cross multiply. 8 sine 35 equals 6 sine beta. Divide both sides by 6. I'm just looking to isolate that beta. That's what I'm solving for. That stuff right there gives me that decimal. Do me a favor, do not round that decimal. Leave that in your calculator and take the inverse sine and paste that whole thing in there. Don't round it, because if you try to round that to, like, say 0.8, your answer is going to be off. It's what's called a compounding rounding error. So if you round along the way and then use that rounded answer to do more computations, your answer is going to be way off. It's going to look wrong. So the inverse sine of that is 49.9 degrees. All right, so is there a second triangle? Let's see. So 49.9 degrees is over here in quadrant 1. Let's see what's happening over here in quadrant 2. If I put that same angle over here in quadrant 2, that is a 130.1 degree angle in quadrant 2, because that's the reference angle. So the actual quadrant 2 angle is this 130.1. So if I take this second angle plus the given angle, that ends up being 165.1, which is less than 180, so there is a second triangle possible. And the last one, remember that when I added those two up, it was bigger than 180, so there was not a second triangle possible. Here, there is a second triangle possible. So This means that I have two options for beta. Beta could be 49.9 or beta can be 130.1. So here's what we're going to do. One triangle. Remember we had A, B, and alpha that was given. Beta can be 49.9 or beta can be 130.1. So what I did was organized it by side. So the left side is one of the triangles, the right-hand side is the second triangle. So I'll tell you what, I'm just going to cover up this side for now, and we'll go through the first triangle. If beta is 49.9, I have that alpha is 35. Let's use those numbers and find the gamma that goes with that. Knowing that the three angles add up to 180, I get that gamma is 95.1. Use the law of sines one more time. That's going to help me find C. So using this law of sines and plugging in for alpha, A, and the gamma that we just found of 95.1, we'll cross multiply. So C sine 35 equals 6 sine 95.1. Divide both sides by sine 35, simplify that, and we get that C is about 10.42. There's the end of one triangle. We're going to need to do all this again, but this time, instead of using beta was 49.9, I'm going to do all this again, but with beta being 130.1. So again, the three angles add up to be 180, so I still have that alpha of 35 degrees. The other beta, the second beta, gamma for this one is 14.9 degrees. And then the law of sines one more time to find C. So here's the law of sines I'm going to use, plugging in for alpha, A, this gamma that we just found of 14.9. Cross multiply, so we get C sine 35 equals 6 sine 14.9. Divide both sides by sine 35, and we get about 2.69 for C. So there's my two triangles. This is a pretty complicated kind of example for these, so because you really have to be on the lookout for those. That, you know, when you solve that law of sines, if it's possible to have that second answer for that angle, you know, that quadrant 1 versus quadrant 2 kind of stuff, that's where it can get kind of messy and complicated here. All right, let's talk about the area of a triangle. You guys probably know the area of a triangle is 1/2 base times height. Why is the 1/2 in there? Well, that's because we look at the triangle as half of a rectangle. So we take a rectangle, we smack it in half, and we know that the area of a rectangle is just length times width. In this case, base times height. So the area of a triangle is just half of a rectangle. Fun fact of the day there. So in this case, if I draw this triangle, we know this is my height. If I draw it so that my base right here is C, okay? And this H right here is my height. The shaded part over here, that's a right triangle. Because it's a right triangle, we know that the sine of this angle right here, notice how this is in standard form, right? A is opposite alpha, B is opposite beta, C is opposite gamma. The sine of alpha in this right triangle right here is opposite over hypotenuse. So it's H over B. So if I multiply both sides by B, I get that H is B sine alpha. That gives me the formula that the area of a triangle can be 1/2 C times B sine alpha or 1/2 BC sine alpha. There are 3 different versions of this area formula. This is 3 different versions of the 1/2 base times height. These versions, different versions, come from rotating this triangle and dropping that perpendicular down to a different side. If I rotated this triangle to where A was my base, I would get a different version of this. If I rotated it to where B was my base, there's the third version. So On your laminated sheet that I gave you, we have these formulas for the area of an oblique triangle. So we have that AB sine gamma, BC sine alpha, and AC sine beta. So let's find the area of the triangle where beta is 124.5 degrees, A is 30.4 centimeters, and C is 28.4 centimeters. Well, I hope it's obvious which of the three area formulas you're going to want to use. We're going to want to use the 1/2 AC sine beta because we have all that stuff. So it's very, very easy, just plug and chug if you know what formula to use. If you don't know what formula to use, this can look really complicated. But we're just going to plug in for AC sine beta, and this is just a straight computation on your calculator. Make sure you're in degree mode when you do it. And you should do that computation as well just to make sure you get the same answer that I did. So I got 355.76, and because it's an area, we know it's in square units, so it's going to be in square centimeters. Now, if we want to find the area of the triangle where A is 20, gamma is 102 degrees, and alpha is 38 degrees, this one's a little harder because if we want to use 1/2 AB sine gamma, and I picked that one because we had the A and we had the gamma, that's almost a problem, right? Because we don't know B. Well, luckily we know how to find B. We know that alpha plus beta plus gamma is 180, so we can find beta is 40 degrees. We can use the law of sines over here to find B, now that we've got beta, so we can cross multiply, and we get that B is about 20.88. And then we can come back over here and say, okay, now I can use the 1/2 AB sine gamma. So sometimes with this area formula, you're given everything and it's a glorious day. You know, it's like, ooh, I just plug everything in and I just get going with the calculator. And sometimes you got to do some of this law of sines and all this other work to get what you need to plug into the formula. So once we plug in that AB sine gamma, so taking B from right over here, then just break out the calculator and you should get 204.24, and it's square units. I didn't give you any kind of unit on there to use. So some of them might be very straightforward, just plug and chug. Some of them you may have to use the law of sines or something else to, you know, this 180 business to be able to find all the information that you need to plug in. All right, last one. Got ourselves a nice little word problem here. A pier forms an 85-degree angle with a straight shoreline. At a distance 100 feet from the pier, the line of sight to the end of the pier forms a 37-degree angle. Find the length of the pier to the nearest foot. Don't worry, I will draw you a picture. I do not expect you to draw a picture from this information. So here's what we're looking at. We got this pier. It's forming an 85-degree angle with a straight shoreline right here. At a distance of 100 feet from the pier, 100 feet away, the line of sight to the end of the pier. So if I'm standing here 100 feet away and I look over here, the end of the pier, that line of sight forms a 37-degree angle. Find the length of the pier to the nearest foot. So we have this triangle then. We know this 85-degree angle. We're looking for this distance right here. I called it A. You can call it whatever you want, but I just called that one A, and then I called this angle alpha because it was opposite. I called this B. This is beta. That's not 85 degrees. Be careful. The 85 degrees is over here. And then the C is 100 degrees, and then gamma is up here. So we are going to have to use something to find the value of A. So first, I went ahead and found beta. Because beta is the rest of 180, so we know this is 85, so this over here is the rest of 180. So I know that's 180 minus 85, so this beta over here is going to be 95 degrees. And then I just went ahead and found gamma as well, because I know that the three just have to add up to 180. So I have 37, this 95 I just found, plus gamma is going to be 180. That gives me a gamma value of 48 degrees. Now I can use the law of sines. Sine alpha over A equals sine gamma over C. I needed gamma because I knew the length of C. I don't know the length of B. So I knew I was going to have to use C, so I knew I was going to need gamma. So I only found beta so that I could find gamma, if that makes sense. So once I have this law of sines, I plug in the stuff I know for it, cross multiply, and then divide by that sine 48, and I get that A is about 81 feet. I don't know why my 1 looks all wackadoodle, but it does. Now don't worry, if I were to give you one like this, I would definitely give you the picture because that's a really tough picture to draw from the information that was given. So, all right, that finishes up this part of 10.1.